How do I know if it's working? Maybe it's going online. Oh, it's open up. What? I think this is as close as it's gonna get, right? Yeah, yeah. I mean, I can do it like here or something. Do you think that would be better? Testing, testing. Oh yeah. Testing, testing. Do I have to hold? Maybe I have to hold it. Is it working now? Okay. Testing, testing. That's good. Oh, yeah, I'm gonna make you guys vote. Yeah, so I think so this was originally what I was planning to talk about, but I was looking over the research interests of the people here, and I thought I would maybe give you another option just in case. So I'll tell you a little bit about what the two options are, and then ask you to vote. Yeah, so both talks are prepared. Oh yeah, I'll say what it is. Oh, so there's no Eisenstein series in this talk. But yeah, no Eisenstein series in this talk. So yeah, so this one is about I guess exceptional motives and exceptional local systems. So families of algebraic varieties whose monodromy group is an exceptional algebraic group. So there's more questions with Serre about this, but now. No. Yeah. Yeah, and so this one is a bit yeah, so the second one would be a bit more related to what I'll talk about in September. So it's about algebraic differential equations and some version of the curvature conjecture for non-linear differential equations resulting from that. I would say that the main difference is that this one will be a bit less technical in the beginning and a little. What? First, second, okay. And so I think it's actually a tie, so it's up to you. Second, okay, great. Excellent. Let me amazing. All right. No, I think you broke the tie. So there was a tie. Yeah. The second top. Okay, great. So let me get the do the people online want to vote? They about you cannot hear. Oh, can you hear now? Oh, and I see this told me. Do we have a okay, do we have a eraser? Someone? We're gonna erase the defunct title. Wait, is there a race? It's the defunct head. All right, let's start. Okay, so before I begin, a warning I've already given to Hi is that I tend to talk very quickly. And over the course of the talk, I'll start sort of reasonably slowly, and then I'll get faster and faster and faster and faster. So one is you have to slow me down. The main way to do that is by asking a lot of questions. So please ask a lot of questions. At least, for quite a while, my aim is to make this talk completely elementary. Every single person here should understand every word I'm saying, and if you don't, tell me. Okay. So let me start with the main motivating question, which is, so given differential equation, well, when can you write down a solution? So when you write down a solution, okay, and so we have very good, at least in a broad variety of settings, we have very good existence theorem solutions. But when I say when can you write down a solution, I mean when can you write down an explicit. And by explicit, at least the classical way of asking this question is, you take this to mean algebraic. So when does a differential equation have a solution to an algebraic function? In other words, it's in the algebraic closure of the field. Let's say in one variable. Now we'll go for that with more generality. Great. So in this, I think the first time this question was kind of formulated explicitly in this way, it was asked by Fuchs in 1870. But I think this is kind of one of the motivating questions of a lot of mathematics since that time. My understanding of the history here is that this question had just been answered for hypergeometric functions by Schwarz a couple of years earlier, and so Fuchs was studying Schwarz's work, and then, well, I think it's very natural once we have that for hypergeometric functions. Well, what about all functions? Why not? Okay, great. So just as an example, well, what's an algebraic function? Every algebraic function satisfies the differential equation. So here's an example of an algebraic function. E to the 2/3 algebraic function. What's a non-example? Well, e to the z satisfies the differential equation. It's its own derivative, but it's definitely not an algebraic function. You might have to think a little bit about why this prove it's not obvious. It's not totally obvious. All of them for everyone in from knows how to prove it, but we'll see at least one kind of proof of this very shortly. Great. So the way I phrase this, it looks like maybe it's a question in I don't know, differential algebra or maybe analysis or something like that. But let's try to understand what kind of question it is. So let's do an example. Here's a different one of my favorite differential equations: c dz minus a over z f of z equals 0. In other words, f prime of z is equal to a times f divided by z. Okay, so what are the solutions for this differential equation? Say it again. Logarithm? Yeah, so it's not quite, I mean, so the answer here, so A is a complex number. So the answer depends on A. And you can write it in terms of logarithms, but is there a, does anyone see the, you didn't think what? Yeah, definitely, d to the A. So the solutions are a constant times d to the constant to be 0. The typical solution is the function, so that's, if you'd like, that's the exponential of a times log c. Also, with an exponential. Okay, so when is this an algebraic function? Yeah, exactly right. Yeah, so this is an algebraic function satisfies a polynomial. If and only if a is a rational. Something going on with this microphone. Here, let me hold it rather than, well, sure. Okay, so great, and this is not so hard to see. So if a is a rational number, you can take this function to the power of the denominator of that rational number, then you get a polynomial. So it satisfies an equation, polynomial equation with polynomial coefficients. If a is not a rational number, the easiest way to see it's not algebraic is to observe that it's not finitely branching in 0. And every algebraic function has finitely many branches. Okay, so I just want to point out this is an arithmetic condition. This is a condition of number theory. The question, is a number rational, is maybe the first question of all of number theory. Pythagoras proved that the square root of 2 is not rational. Maybe not Pythagoras. One of the Pythagoreans, I guess, proved it and then was thrown into the ocean. Okay. So I guess for many people, I think this is probably a disturbing realization that this question is really one of number theory. Probably for the people in this room, it's more of an exciting realization. Okay. So I think maybe probably already by the late 19th century, this was known to be kind of a question of a number theoretic nature. And at least for linear differential equations, I think there's a very well understood conjectural answer to this question of Fuchs, called the Grothendieck-Katsky curvature conjecture. But I want to explain that. So I think here's kind of the main conjecture in the subject. So I think the origin is that Katz was studying this object called P curvature, which we'll talk about more later in the talk. And he was presenting on it at the IHES with Grothendieck in the audience, and then Grothendieck asked the question verbally that I'm about to write down, but I think it first appeared in print in the work of Katz. Okay, so the conjecture is the following. So suppose A is a n by n matrix of rational functions. I'll just say, I'll give them rational coefficients for now. It's easy to avoid this, but make the statement a bit simpler. So the conjecture is the following. So all solutions to the linear ODE, d dz minus a f of z is 0 are algebraic. The solutions are vectors of algebraic functions. If and only if the following condition holds, so d dz minus a to the p is identically 0 mod p for almost all primes p. Okay, so let me briefly explain what this means. Well, this is a n by n matrix of rational functions with rational coefficients. There's only finitely many primes appearing in the denominators of those coefficients. So for all but finitely many primes, it makes sense to reduce this matrix mod p, and then you get a differential operator on rational functions over fp. And I'm asking that differential operator be identical to 0. Okay, yeah. So I'll say a bit about what's known, but maybe let me just say the forward direction. So if all solutions are algebraic, then this holds is very easy. So if you try, you will succeed within the next 5 minutes. very little is known about the backwards direction, but I'll try to give you some sense of what's known. I also, in a little bit later in the talk, I want to try to explain a bit more, a bit of intuition about what this identity means. But hold on, we'll get there. Okay. They're the same. They're the same. That's a bit. I'm saying the pth power is 0 mod the same. Are there any questions about this statement? Okay, so let me say what's known about this conjecture. So I think it's fair to say that it's basically open. There's very few cases that are known. So I think the strongest evidence for this conjecture is the theorem of Katz from 1972, which is that it's true for Picard-Fuchs equation. Like one can generalize this conjecture to the setting of vector bundles with connection. The right thing to say is yes, monoid connection. If you don't know what this is, don't worry. You should think a Picard-Fuchs equation is the differential equation satisfied by a function which is given by integrating a family of algebraic. So the differential equation is satisfied by period integrals. Okay. So the other main case that it's known for is due to Chudnovsky, Andre, and Bosch. So it's true for ODE with solvable monodromy. So, for example, the case where this matrix A is upper triangular. So that includes, in particular, the case of order 1 ODE, where n there, that matrix is a 1-by-1. I think this is essentially a complete list of the cases that I think I'm sure you know. Be a couple other things, like I guess Katz or hypergeometric. Okay. But yeah, for example, for general second order ODE, it's totally open. Great. Okay, so this conjectural answer, I think, is kind of a unsatisfying answer to this question of Fuchs. And there's two reasons why. So, well, the main one is that it's a question about it's a conjecture about linear ODE. Right? And so there's lots of interesting differential equations which are nonlinear. Question. What about nonlinear ODE? I'll talk near the end of the talk about my favorite nonlinear ODE. Right. So in this case, there is a conjecture. So Eck et al. Baron. Taylor give a conjecture, so an analogous conjecture for when all solutions are algebraic. You should think of it as completely analogous to what I've written down over there. I won't write down the form of the conjecture. In September, I'll explain how to prove this conjecture for a large class study. That's what I'll talk about, in a month and a half or so. But there's something still unsatisfying here, which is especially for nonlinear ODE. It's very easy to write down nonlinear ODE where a general solution is not algebraic, but where there's some special sporadic solution. So one might be interested in understanding. Well, you give me an ODE, you give me one specific initial condition to solve for. When is that solution? When is that one solution? When is one? solution algebra. So for example, like suppose someone gives you the Taylor expansion of a solution to your differential equation, can you tell that it's algebraic? That's a question that was asked by Richard Stanley, among others, in the context of combinatorics, where you kind of often are in this situation where you have some explicit power series, maybe a generating function that satisfies a linear or nonlinear ODE. You'd like to understand, is this an algebraic function? Because that gives you like a recursion of things to take. All right, so I want to propose an answer to this. Okay, are there any questions before I do that? So maybe let me say like the kind of answer I want is like a criterion in terms of Taylor coefficient. I mean, in particular, I want something like really simple-minded. I think you might have had a little bit of trouble explaining to, I don't know, Gauss or somebody why they should care about this kind of maybe more abstract seeming conjecture, but I would like something that I could explain to Gauss. I think I would be happy with it. Okay. All right. Okay, so in order to answer this question, we have to find a property of algebraic functions that is not satisfied by all functions, right? And then we kind of hope that it's sufficient to characterize algebraic functions among solutions to differential equations. Okay, so here's I think the best theorem along these lines that I know of. So of its Eisenstein last theorem. 1852 or 1853? 1852. Okay. Here's the theorem. I guess what I'm about to write down is kind of a simple version of the theorem. It proves a little bit more. So let f of z be a power series with rational coefficient. The Taylor expansion of an algebraic function. Say here, f of z sum a n dn over all positive or over all non-negative. Great. And so here I'm just saying when I think Taylor expansion of algebraic function, I'm just saying this power series satisfies a polynomial with polynomial coefficients. So then what Eisenstein showed is that there exists positive integer n such that all of the Taylor coefficients lie in the ring Z adjoin 1 over n. So another way of saying that is that only finitely many prime numbers appear in the denominators of this infinite collection of Taylor coefficients. This is not a very hard theorem. If you all go home and try to approach it with the kind of more modern algebraic geometry you will succeed. Eisenstein did not quite succeed, so he wrote this paper in 1852. I'm calling it his last theorem because it's the last paper he ever published, 2 months before he died of tuberculosis at the age of 29. And he gives a sketch, which is, I would say, close to correct, but probably not quite correct. And then Heine, a couple of years later, wrote down a complete proof of this theorem. And there's kind of an interesting mystery here. So in this 3-page paper where Eisenstein published this theorem, he says something like, I found some wonderful applications of this result for the study of solutions to differential equations whose Taylor expansions are easy to understand, but which cannot be written down simply in closed terms. And then he doesn't say what those applications are. And then he died, so we don't know what that. So my guess is that he had figured out how to classify algebraic hypergeometric functions, which if that's true, it would mean that he'd beat Schwartz to the punch by about 20 years. But of course, we don't know. I think this is really interesting mathematical mystery, and I've spent a lot of time searching through Eisenstein's complete works and letters, trying to get some hints and stuff of what the solution to this mystery is. But if you are able to find any bits of correspondence from Eisenstein that I might have missed, please let me know. Okay, so the question is, well, is the converse to this true? Well, so it's definitely not true that if you have some random power series, all of the Taylor coefficients lie in here, then it's algebraic, right? I mean, there's uncountably many power series. These coefficients are like 0 and 1, and only countably many algebraic functions. So the converse to this theorem can't possibly be true naively, but you can ask, well, does this characterize algebraic functions among solutions to algebraic differential equations? So suppose you have a solution to an algebraic differential equation like this one, and you know that its Taylor coefficients only have finitely many prime numbers appearing in the denominators. Does that tell you that your solution was algebraic? And so there's no obvious counting obstruction because there's only countably many algebraic differential equations. So it could be conceivable that some criterion of this nature characterizes algebraic. So does anyone know the answer to this question? Or does anyone have a guess? Yeah, so the answer is no. So let me give you an example. Sorry, were you saying no, you don't have a guess, or your guess is no? But, okay, good. You're right. Okay, so here's one of my favorite functions. So let's take f of t, be 1 over pi times the integral from 0 to 1 of dx over the square root of x times 1 minus x times, make sure I'm getting this right, times 1 minus tx, right? So this is an elliptic integral. It's an example of one of these period integrals which satisfy the Picard-Fuchs equation. Here, it sort of obviously satisfies a differential equation because it's an integral of a nice algebraic function. This satisfies the second order ODE. And let me tell you its Taylor expansion. 1 over 16 to the n times 2n choose n squared d to the n. Here's the Taylor coefficients they lie in z adjoin 1. The 2n then is an integer, so the only source of denominator 1 over 16 to the n. Maybe just for concreteness, let me write down the ODE it satisfies. And here I have to actually look at my notes. So it satisfies 4t 1 minus t f double prime plus 4 times 1 minus 2t f prime minus f equals 0. This is an explicit counterexample to the sort of naive converse to this theorem. Okay, so the answer to is there a converse to Eisenstein's last theorem is no. The talk is over. I'm just kidding. Okay, so I want you to observe something, which is this behavior. Here we took the Taylor extension of this function at 0, right? And this differential equation behaves differently at 0 from at most points. But it's singular at 0. Right? When you plug in 0 here, this coefficient vanishes. So yeah, so to study the singular point of an ODE, you want it to be monic, so you divide by 4t 1 minus t, and so you see that the singularities of this ODE are 0, 1, and infinity. This is singular. 0. Great. And okay, so you can start looking at a lot of examples of this phenomenon. We actually know a lot of solutions to ODEs whose coefficients satisfy this property. There's a name for them. They're globally bounded G functions. Their study, well, arguably goes back to Eisenstein, but they were very heavily studied by people like Crystal and Andre in the 70s and 80s. Work, I guess. Maybe Viegel too. I'm sorry? So I'm saying this is not an algebraic function. I guess I didn't prove that for you, but it has this property that it's a solution to an ODE, all of whose Taylor coefficients lie in kind of you join 1/2. So yeah, maybe I should have said this. This is not algebraic. Okay, and there's a lot of ways to see that. Again, you can kind of see that it's not finally branching. Okay. Okay, so let me tell you the conjecture. So I think if you start to look at examples of this phenomenon, so solutions to algebraic differential equations, which are, have this property that their Taylor expansions only have finitely many primes showing up, they're not algebraic, you start to notice that they all have the property that you're taking the Taylor expansion or the singular form. So here's the conjecture. Great. So vector. I'm going to attribute this to Josh and myself, but there's kind of precursors and work of Andre and Bristol and other people. And to be honest, I find it kind of unbelievable that surely someone in the 19th century thought about what I'm going to write down. I haven't been able to find it. Okay, so here's the conjecture in its basic form. So suppose we have a power series f of z, which is sum an d to the n, d double bracket z, satisfies the nth derivative of f is some function of the f of z. I'll say that's my first derivative of f. D is a rational function, and d y0 through yn minus 1. And I want to assume that that this differential equation is non-singular at the point that I was mentioning, that u of 0, f of 0, all the way up to f minus 1 of 0 is defined. So just to be explicit here, G is the ratio of two polynomials, and I would like the denominator not vanish. So then the conjecture is that the following are equivalent. Okay, so one is f is algebraic. The Taylor expansion of an algebraic function, or equivalently, it satisfies the polynomial with polynomial coefficients. So two, well, this condition due to Eisenstein holds. So there exists an n bigger than 0, such that all an lie z adjoin 1 over n. And I'm just going to add one more condition, which you should think of as a little bit technical. But I want to write it down so that I have something that implies all the conjectures in this area. So there exists some function omega from primes to z, such that the limit, if p goes to infinity, of omega p over p is infinity. It's growing slightly faster than a linear function, so think like p log p or something like that, p log 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 p, something like that. So such that a0 to a omega p lie in the parentheses. Okay, so what this means is that the first like p log log p coefficients don't have a p in this number. So in other words, you can check. So the conjecture is kind of that you can check whether a solution to a differential equation is algebraic just by looking at the first few coefficients and checking whether a p appears in the denominator, where the first few depends on p. Slightly more linear way. Okay. So I want to point out, so in this Grothendieck-Cat p-curvature conjecture, you should understand this condition here as being basically this condition in 3. So when you write down the Taylor expansion of a solution to a differential equation, you're taking things like this operator to the n over n factorial. So in particular, when you say you take this to the p over p factorial, this condition tells you you don't get a p in the denominator. So in fact, if this condition holds, you can take omega to be like p squared. So this is really much weaker than the hypothesis. Great. Okay, so this is the conjecture. Maybe my suggestion is just to ignore point 3. It's something I'm writing down to make sure I'm giving a statement that that implies the growth in Katz p curvature conjecture. And every proof I know, like every case of this I know how to prove. All you need is to get condition 1 is condition 3. You don't need the full force of condition 2. But I think it's a bit easier to think, just like forget about 3, and 1 and 2 are the more elementary conditions. The conjecture is that if you take the Taylor expansion of a solution to an algebraic differential equation at a non-singular point, it's algebraic if and only if this condition on Taylor expansion is only finitely many primes appear in the denominator, Taylor coefficient. Okay, maybe let me pause for a minute and see if there are any questions about the statement. Yeah, so the reason this is not a counterexample is because it's singular at 0. Yeah. And so the conjecture is really that that's the only thing that can go wrong. No. So for all large groups. I mean, since I said this function is valued in z, I think, well, if it's -1 or something, then you get it. Well, this is not a condition anymore. So I think depending on how you interpret this, which is not necessary. I'm sorry, say it again. Yeah, so here, yeah, this solution, yeah, the only prime that is the problem is 2, but the reason it's not a counterexample to the conjecture is this. Oh yeah, yeah. So condition 3 is satisfied. Yeah, it's the thing that's not conditioned is not satisfied with this. And that's really nice. Okay, so this is some really, I think, really elementary conjecture. I think that Gauss or Eisenstein or someone could have thought about it. I don't know if they could have proved anything about it. Because we'll see that the things I know how to prove this really require some quite modern ideas. Get a copy theory of things. I think you should just think of it as an analog of curvature vanishing. It's a consequence of p curvature vanishing. It's a bit stronger. So the main way this is stronger is that this is really just a condition on one solution, whereas you should think of this condition in the growth in Katz conjecture as saying all solutions to your differential equation property. So it's kind of a flip one. So this is yeah, I think you should think of this is like basically the weakest thing I could possibly think of that would imply 1. Yeah, this is my conjectural answer to Stanley's problem. Okay, so maybe let me just, I've said a couple things. Let me just write them down on the board. So the first remark is that this implies the Gross-Katz conjecture. So it's stronger in at least 3 ways. So the first way is that it's about nonlinear ODE as well as linear ODE. It's about one solution to your ODE rather than all solutions. And then this condition 3 is a bit weaker than what you get out of Katz. Let's see. So for linear ODE, I gave this sort of funny attribution to this conjecture where I put Andre Stoll here. So for linear ODE, this is some version of a conjecture that's not exactly made by Andre and Stoll. So it's a situation where Andre says something like, based on the work of Cristol, it might be natural to ask if something. So for linear ODE, it's close to a remark of Andre and Cristol. But I think there exists a paper calling some version of this for linear ODE, I guess the equivalent in 1 and 2 for linear ODE, the Andre and Cristol. Great. Cool. And maybe let me just make one remark. So I tried to give you a really elementary formulation here where you just like write down a classical ODE that you might see in like a second-year undergraduate ODE course. But I mean, of course, one can make this more general. So the growth in Katz conjecture, as you usually see it, is something about vector bundles with flat connection. So here, so this can be generalized to, I would say, the sort of best generalization of the algebraic differential equation is an algebraic foliation. So this can be generalized to the study of algebraic foliation. If someone gives you a foliation on a smooth algebraic variety, you can ask when is a given leaf of that foliation an algebraic subvariety, and there's a version of this conjecture for that. I'll talk about that a little bit later in the. Okay. Are there any other questions about the statement? Yeah. This, you mean this and the order of the ODE? Oh, like what can happen? Yeah, I mean, I think the thing that the reason I'm oh, I see. Yeah, I mean, we know things like about how quickly the p-adic valuation can grow. So there's Losch gave bounds on this. So it's pretty elementary. It's like you basically study Taylor's formula. Beyond that, in the linear case, that sort of rate of growth can tell you something about the geometry of a, let's say, a Picard-Fuchs equation, but I don't think I have a good answer beyond that. Like I think for general ODE, yeah, we have a good understanding of these growth rates. I don't work with them. Maybe just a small digression is I said you could see this conjecture in a second year ODE course. So when I was in undergrad, I really did not like differential equations. I never took a course on differential equations, but somehow I got obsessed with them. So I spent a lot of time in the last 2 years like learning this like basic ODE. It's really a beautiful subject. So a lot of the story really built that over Frobenius, other people in the late 19th century, and it's a beautiful classical theory. Okay. Okay, so for the rest of the talk, I want to give you some evidence for this conjecture. So what do we know how to prove? Yeah, so maybe let me pause one more time for questions about the statement. So speak now or forever hold your peace. I've been told that when I ask for questions, I should pause for 7 seconds. I then always fill by saying this fact that I should pause for 7 seconds. All right, you all understand the conjecture. Great. Let's see some. Maybe I'll start with evidence over here. Okay, this is section 2 of the talk. I want to start with linear. So as far as I know, despite the fact that some version of this conjecture appears for linearity, I'm not aware of any literature on it for linearity. So I want to explain some statements. And in particular, I want to say, and there are cases where the Grothendieck-Katz conjecture is known. We do not know this conjecture for those cases. So this is strictly stronger than the Grothendieck-Katz conjecture. And the reason why is that, like for example, when Katz proves the Grothendieck-Katz conjecture for Picard-Fuchs equations, he uses that this condition 3 is satisfied for all solutions. If you just know it for one solution, that's not enough to run itself. So let me start by giving you a theorem. So this is joint work with Josh Lamb, like everything in the top. So the conjecture is true for the ODE star that I wrote down earlier. So here, what does this mean? So what I mean is that take this differential equation, take the Taylor expansion of a solution at any point which is not 0, 1, or infinity. Then, well, because we know the solutions are not algebraic, as long as the solution is the non-zero solution, or not algebraic, what that means is that infinitely many primes appear in the denominator of the Taylor coefficient. In other words, one way of saying that is if f of v minus a 0, 2 zeros from a from a n b minus b0 to the n, the Taylor expansion for z0 not equal to 0 or 1, infinitely many primes. Here in the denominators of the AI. Okay. Okay, so what kind of theorem is this? I mean, the proof is a little bit fancy. I'll say a little bit about it later, but I just want to stress this is like a really elementary statement. So to write down these Taylor coefficients, you just like solve a linear recursion. So it's saying I have some explicit solution to a linear recursion, and no matter how I no matter what the initial conditions are, there are infinitely many primes varying the denominator of the solution. Okay, I would love an elementary proof of that fact. I know an elementary proof for z0 is 1/2, which you can it's pretty easy to see because you can use the fact that f of z is related to f of 1 minus z. But for all of those z0s, I don't know a simple argument. Okay. So this is some very special case. Let me tell you what it's a special case of. So 0 a prime, so the conjecture is true for elliptic integrals. Special kinds of Fuchs equations, solutions to regard Fuchs equations associated to multiple forms. And some other cases. Sorry, I'm running a little low on chalk here. Okay, so this is kind of an imprecise statement. Let me give you a precise statement. I'm just saying there's sort of a bunch of examples which are related to elliptic curves that we know how to handle. So this is what we really do in this theorem A is that the conjecture is true for different equations in the tensor category generated by the Fuchs equation associated to a family of genus 1. Yeah. Mm-hmm. Yeah, so if you take right, so you have to figure out how to convert a linear differential equation into this form. So given a linear ODE, there is some equation of this form. You can like choose a cyclic vector and do this usual trick where you kind of turn a first order ODE, sorry, a linear ODE in many variables to a higher order ODE in one variable. And then it's true for that ODE. If only it's true for the original ODE. So there's for each linear ODE, there's one. Yeah. Yeah. So there's a way of turning a sort of system of ODE into a higher order ODE. Yeah. So for linear ODE, you can get a first order ODE in many variables. That's the same data as a higher order linear ODE. Like it's basically the theory of companion matrices. Yeah, in that case, the function is some linear function in the last variable. Yeah, it's a linear except in this. Yeah. That's right. That's right. Yeah. Oh, then it still implies the big picture. Yeah. Yeah. So for each case of the GK conjecture, there's one G here. Yeah. Great. Any other questions about this? Okay. So if you don't know what a Picard-Fuchs equation is, I'm going to start explaining that now. Okay, so I want to, this is sort of the first evidence. I think this is the first thing that can convince me the conjecture was true. And it's sort of like maybe the first thing we try. I want to talk about our best attempt to prove a stronger theorem for linear ODE. So in order to do that, I have to explain a little bit about what Picard-Fuchs equations and what Gauss-Monod are. No. So this is completely different. I'm sorry? Take a family of genus 1 curves to corresponding Gauss-Monod connection. And there's a version of this conjecture with a flat bundle that you'd like, if you're over the projective line, you get it on a second order ODE. And I'm saying it's true for that ODE and all of the tensor powers. Okay. So maybe I should leave the conjecture up. Okay, so I want to go on a slight digression. Where do differential equations come from? So right now, we just don't know enough to prove a conjecture like this for arbitrary differential equations. We need differential equations with a different structure. And so I would like to explain where in algebraic geometry you find differential equations. If you have a differential equation which kind of comes from algebraic geometry, it's a lot of structured things I do exploit. So the proof statements. So of course, this is a special case. Elliptic integrals are a very special case of differential equations coming from algebraic geometry, but there are others. So here's a slogan. Differential equations come from topological invariance of algebraic variety. So let me give you an example. So here, suppose x to s over c with a smooth proper morphism. What's a topological invariant? This algebraic object, or the fibers of this map? I think it's cohomology. Here, I guess I'm looking at the analytic topology. Is this okay with everyone here? If you should interrupt me if you don't know symbols. Okay, this is the local system on S, whose fiber over a point is the cohomology. The cohomology of that local system by Erismans that are on this, because this map is smooth and proper, so it's a fibration. Okay, so this is not yet a differential equation, it's a local system. How do we make I guess I should say S should be smooth. So how do we make a differential equation over it? Well, the simplest way to do it is let's make it into a vector bundle. OS, and it has a connection on it given by the Gauss-Monod connection to the identity tensor, the exterior derivative. This is a flat vector bundle. If S is an open subset of P1, a flat vector bundle is just the same thing. In other words, you choose a cyclic vector and use that property. Okay, so there's a miraculous fact So the description here I've given is very analytic, right? I use the analytic topology here. But the miraculous fact due to Katz and Oda, although of course in some sense, it was known to people like Picard and Fuchs and Poincaré, is that this flat vector bundle is algebraic. It is an algebraic flat bundle, or do it as an ODE of algebraic ODE. It's what that means is that this bundle is in particular the analytification of an algebraic bundle on S, a natural one, and this connection is itself algebraic. Structure constants are regular function on S. Okay. Great. Okay, so this is an example of a so yeah, these are called Gauss monotromy. The flat bundles which arise this way are called Gauss monotromy connections. I told you earlier that Katz had proved the p-curvature conjecture for Gauss monotromy connections. And these are the object and the differential equations associated with these linear ODE. I gave you a slogan. I said ODEs come from topological invariant algebraic varieties, and here I did probably everyone's favorite topological invariant, which is homology. There are other topological invariants of algebraic varieties, other invariants in topological spaces. So can anyone name one? Say it again. Yeah, so can anyone give, so someone said something. Yeah, the fundamental group, yeah, exactly. So right, so here if we take homology, we get a linear ODE. If we're looking for a nonlinear ODE, we should take a non-linear invariant. So here we can take, well, maybe pi1, let's fix a point here, pi1 of a fiber. This is a little bit too nonlinear. I don't know how to make a ODE directly out of this. But if you look at more linear object, you can take the space of representations of this group. Okay, so this is at least a more algebraic object. I mean, this is a discrete group. This is an algebraic stack. And if you'd like, you can semi-simplify, and then it's really the points of a natural algebraic variety. Okay. So well, here I've done something on a fiber. That's not quite the same as what I did here. So here I took the local system on X. What's the analogous object here? So you can think of this data here as capturing the action of pi1 SS on the homology fiber. And there's an analogous object here. So in other words, pi1 of the base acts on the space of representations of pi1 fiber. Why is that? Well, it's a little exercise to see that this group has an outer action on this group. Why? Well, if you have like a loop upstairs and a loop downstairs, you can drag the loop upstairs around the loop downstairs, get a new loop. That doesn't give you a well-defined element of pi1 because you might have lost the base point. That's enough to get an outer action. Outer action descend to an action on isomorphism, flat piece representation. So if you haven't seen this before, you can take my word for it. It's a little exercise, which I don't want to do. Okay. Great. Okay, so great. So let me kind of use this now. So now we can take representations of pi1 of the fiber and multiply them with the universal cover of S. And well, pi1 acts on both of these things. I just told you pi1 acts on representations, pi1 acts on the universal covers. So I can quotient by the diagonal. This maps to S. What is the structure of this space? This space is locally a product. In other words, the horizontal foliation. This carries a horizontal foliation. It's called the isomonodromy foliation. Simpson says this is the non-abelian analog of the Gauss monodromy. Okay, so I want to spend some time on this because you probably have not, maybe many of you have not thought about this much before. So first of all, I am going to admit to a lie. So in general, this space is not smooth. If you want to work properly, it's not even a scheme, it's a stack. So the right way to say this is that this is a crystal over S. So this is something that Simpson works out of with the complex numbers. But the other issue here is that the way I've described this, it is not a algebraic ODE. So I want to explain how to make this an algebraic ODE. Okay. I still don't think this will cover it. Cover it. So the algebraic version take moduli spec m to rom of x over s. S. So you can think stack of flat bundles on the fibers of x over s. And this carries this. I'll write the graph statement. This is a crystal over S. You should think this means this carries an algebraic foliation. Okay, so what are the leaves of this foliation? If an object equipped with a differential equation, what are the solutions to that differential equation? So the solutions to this differential equation, or the leaves of this foliation, are families of flat bundles whose monodromy is locally constant. In other words, what do I mean by this? Well, this is a smooth proper morphism. All the fibers are homotopy equivalent. They all have the same fundamental group. So if you have a flat bundle on one fiber, you get a representation of pi one. If you have a flat bundle on another fiber, you get a representation of pi one of that fiber. Those groups are the same, right? So you can ask, are those representations? So this is the ODE whose solutions are families of flat bundles, or people like families of global system, whose monodromy representations are not changing as you vary from fiber to fiber. But here, this is why I say ODEs come from the topological invariance of algebraic varieties. If you have a family like this, the topology isn't changing, but the algebraic structure or the complex structure is changing. And these ODEs measure how the algebraic complex structure is changing relative to the topology. Great. Let me give you an example. Sorry, maybe I should pause for question. I guess I've already given you an example of a Gauss-Monin connection. So here, this is the Gauss-Monin connection or differential equation associated to this ODE satisfied by this function, which is, if you'd like, it's the corresponds to the family of elliptic curves y squared equals x times 1 minus x times 1 minus px. So let me give you an example of an isomonodromy differential equation. I'll give two examples. So example, maybe the most famous example is the Penalove-6 equation. So I'm not going to write it on the board. It would be like 2 lines long, but you can go to Wikipedia and see the 2-line long equation and feel excited about that. But here's one I like more. It's called the Schlesinger system. That the Penalove-6 equation is a special case. So I'm going to let B1 to Bn Br the n by n matrices such that sum of Bi is 0. For matrices of holomorphic functions. And then so So here, these are functions of lambda 1 through lambda n, lambda 1 through lambda r. And I want to tell you what the derivative of pi is with respect to lambda j. And very simple formula. So if I is not equal to j, get the commutator of b and pi and dj divided by lambda I minus lambda j. Then I have to tell you what is the derivative of pi with respect to lambda I, and that you can figure out from this equation just by differentiating it. You want the sum over I of, sorry, sum over j of d lambda I db j d lambda I equals 0 for all I. Okay, so this is some nonlinear system differential equations. I claim it is an isomonodromy differential equation. So let me tell you why that is. So given a sequence of matrices like this, you can form a flat connection. You can form a differential equation. You take, given these, you take d dv plus some di over d minus lambda I f equals 0. This is a differential equation on the projective line. This condition is that it's non-singular at infinity. Okay. So this differential equation gives you a monodromy representation. You take local solutions, you can analytically continue with them in a loop. You get new local solutions. That assigns to, well, I said given a basis of local solutions, you get a new basis of local solutions by analytically continuing along a loop. So to each loop, I've associated a change of basis matrix. A way of assigning a matrix to a loop is a representation of pi1. So I've said, well, here to this data, I get a representation of pi1. And the fact that this is a solution to this differential equation, to this, let me call this dagger, this is a solution. So being a solution, I guess these are functions of lambda. Solution to dagger is the condition that the monodromy representation is independent of lambda. In other words, for each lambda, I get a differential equation. For each tuple of lambdas, I get a different minus the lambda i's. And I would like, as I move the lambda i's around, for the monodromy not to be changing. Here, Schlesinger in 1912, I think, wrote down this condition, which is equivalent to that. It's, by the way, it's really fun to derive this. So when you go home later, try to prove that these two conditions are the same. It's a little tricky, like you have to think about it in the right way, but you'll succeed. Oh, so this is, I think, this is maybe the original source of isomonodromy equations. Maybe a small historical note is Penlevet did not discover the Penlevet-6 equation. It was discovered by Richard Fuchs in 1905, but unfairly named after Penlevet. Okay, and Fuchs also found the Penlevet-6 equation in this context, but he was actually studying isomonodromy in 1905. So here, yes, this is a differential equation. So this lives on P1 minus lambda 1 with lambda r. So here the lambda is a tuple of complex numbers. And so here I get a family of differential equations on this family of varieties. Yeah, lambda is a parameter, yeah. I'm asking, yeah, as I move the lambdas around, I want the, yeah. Great. Okay. So I think this is kind of these are the two main examples of differential equations I know of that have some algebra geometric structure. So Gauss-Model connections and this kind of non-abelian version of the Gauss-Model connection, which captures the monodromy of differential equations itself. The BIs are functions in the lambda. Here, these are, yeah. Here, they're functions on, so they're matrices of functions on affine space with coordinates lambda, 1 to lambda r. Yeah. There's some beautiful classical mathematics that I think maybe has not been studied as well as it should be by algebraic geometers. So Malgrand, who is student of Grothendieck, worked on this sort of thing a little bit. The Japanese school that studied with Kimbo and Uena and so on. But I think there's a lot of algebraic geometry left to do with these. Okay. Great. So before I continue, let me just say a little bit more about these ODEs. So if someone gives you a differential equation, to write down a solution, you pick an initial condition, and then you solve it subject to that initial condition. So what are the spaces of initial condition? So the initial conditions, so here we're in this setting. So for Gauss-Modern connections, with our Brooks equation, the initial conditions are, well, just the cohomology of a fiber. So in other words, I can take the given an element of the cohomology of a fiber, I can ask for a solution around that one. Okay. And for isomonodromy, the initial conditions are well, flat bundles on a fiber, or representations of pi one. So in other words, given a flat bundle, to solve an isomonodromy ODE, I want to write down a family of flat bundles on the nearby fibers with constant monodromy. Here, you give me one of these, write down a solution to this ODE, I'm writing down a family of differential equations whose monodromy equation is independent of lambda. Great. So this is the setup. I want to tell you theorems about both of these situations, but maybe now would be a good time for a 5-minute break, and then we can come back and do some theorems. How are you guys doing? Little mental, yeah. Oh. Yeah, you got to slow them down. Oh yeah, so here I'm saying what the initial conditions of these things are. So yeah, for isomonodromy, the initial conditions, an initial condition is a flat bundle of fiber. Yeah, so right. So if you want to solve a differential equation, if I want to ask you to solve a differential equation, I better tell you the initial conditions about which you're solving it. So I'm saying here for an isomonodromy equation, I give you a flat bundle, and you're supposed to return a family of flat bundles, whose restriction to that point is the one I started with, where the monodromy representations come. Yeah, so this thing is some kind of non-abelian version of Gauss-Modern connection, but in general, it's a highly nonlinear differential equation, which, you know, it's yeah, its solutions cannot be written in terms of kind of a wild up. So the isomonodromy ODE is yeah, so I mean, what it really is a foliation on the modular platform. Yeah, so just as an example, the Pendelwey-6 equation, it's a theorem that a generic solution to the Pendelwey-6 equation cannot be written down in terms of solution to linearity. Yeah, so you start with one flat. Yeah, right. So here I'm saying I give you the value for, I give you the BI of some lambda naughts at some point, and I want you, so that is a linear ODE, but the solution to my isomonodromy equation is not a solution to a linear ODE, it's a family of linear ODE. Right, so that is, you know, this is clearly a nonlinear differential equation. It's a common thing. I mean, it's a theorem that these things, for Pendelwey-6, a general solution cannot be written down in terms of solutions of linear ODE. Yeah. Oh, so I'm the simplest way to say it is this is not a linear ODE. Not a linear ODE. It's a commutator to me. Gauss-Modern connection is a linear ODE. It's a flat bundle. Yeah. And then the isomonodromy is not a linear. Yeah, you should think of it as being kind of one categorical level higher. So it corresponds to this action of pi one on a variety, but this variety has no additive structure. Yeah. Yeah. So it's something, yeah, I mean, it really is nonlinear in the sense this is kind of nonlinear representation. That's right. Yeah. I think it's a very, I'll try to convince you at the end of the talk that it's a very important talk. Oh, two. Thank you. It's great for me to give this long talk. I can say everything I want to say. It's probably bad for you guys, but I'm yeah. Okay. Gauss-Monod is something on the base. So Gauss-Monod, so you should think of it as you have a flat vector bundle on the base. You can think of that, you take the total space of the flat bundle and there's a foliation on that. Right. So here the analogous object is this moduli of flat connections on X over S, and that has a foliation. So yeah, you should think this is analogous to the Gauss-Monod connection. It's cohomology with the Gauss-Monod. Yeah, so they're both objects over F. That's a great question. There's actually a theory over an arbitrary base. So of course you have to describe isomonodromy in a different way, but we do that in our work. I mean, of course, in some sense, it's implicit in work of like Galois, the theory of crystals. Yeah. So of course, yeah, to make sense of, I guess I made a claim here that this is a kind of algebraic crystal. And in order to study these conjectures, you need to descend to finally generate field. So we showed that it does. Yeah, so in fact, a lot of what we have to do to set this up is just develop foundations for isomodel. I don't. I have to look at my calendar. I'm not sure if I have to be in Europe soon. What? I know. I'm just not sure if I don't know, think I am scheduled to be. And probably I am, but I don't remember my travel. So, okay. Should I start again? I guess. Yeah, oh yeah, I didn't tell you what the family is. So here, okay, you caught me in a slight lie. So this is a version where you don't take X to be smooth and proper. This is what you get if you take M0 n plus 1 mapping to sorry, it's M0 R mapped to M0 R minus 1. Yeah, so here I'm taking the universal family of marked P1s, and then here, well, this is the connection on a marked P1 with regular singularities infinity. Yeah, so there's a whole version of this theory for regular singularities. Everything I'm going to say works in that setting, and we written it down in that setting, but I decided not to do it in the talk. Yeah, so here you should think the S is M0R and the fibers are P1 minus 20. Any other questions? Yeah, so I would say almost all classical work on isomonodromy is in this setting, but we develop it in a bit more relative. That's a great question. I will answer that by the end of the talk. sorry, so I'm erasing some evidence for conjecture at the bottom board here. So let me give you some new evidence to make up for that. Theorem B. So I'm still in linear ODE, I guess. So the linear ODE on the board is the Gauss-Monod connection. So let me tell you what we can prove about Gauss-Monod. Unfortunately, we cannot prove this conjecture for Gauss-Monod connections full stop. I think there are good reasons to believe that one needs genuine new ideas to do that. That would imply the p-curvature conjecture for some ends of Gauss-Monod connections, and we don't know how to prove it. That's a kind of a famous open problem. Let me say what we can prove. So we can prove it for certain initial conditions. Let me remind you. So an initial condition is an element of the homology of the fiber. Here, let me give you the setup. So X, S, smooth proper. This is let's say smooth over Q. You can put any finally generated field here, and you just have to slightly modify the conjecture, but I'm not going to do that. Simple Q. So one gets associated to this is Gauss-Monod connection. The Gauss-Monod connection. So I can take S to be an open subset of P1, and then we're really in this setting where we have a linear ODE, one variable. Right, ODE means one variable, the linear ODE. So then I want to define a subspace of the initial condition. So I'm going to take the conjecture true for Taylor suspensions of solutions to solutions to this differential equation, now Gauss-Monod S equals 0, about some special class of initial conditions. So initial conditions, I shouldn't have done S here. But initial conditions in the image of the cyclic pattern. Here, I'm doing a bit more than like the honest cycle class map. I'm allowed to like see linear combinations of cycle classes. It's actually going from here to here, so allowing yourself to take linear combinations is very hard. That's the bulk of the proof for this though. Okay, so we can't quite prove this conjecture for all solutions to Gauss-Monod connections, but we can prove it for solutions with some algebraic geometric meaning. I don't think I have time to say much about the proof, but let me just say that the proof uses, so this input from both Hodge theory and some Getic Hodge theory, so continental phi theory. This conjecture, the proof of this theorem uses like 1970 mathematics, I guess. So probably Katz could not have proved it when he was proving the conjecture for Gauss-Monod connections, but it's not, doesn't require things that are too modern, just like sort of the beginning. Yeah, right. Great. So I think this is kind of the main evidence we have for these conjectures in the linear setting. So I want to spend the rest of the talk talking about the non-linear setting. Yeah. Yeah, so I'm saying I have a family. I take the Gauss-Monod connection coming from the even homology, and I take the Taylor expansion around the solution, which is a linear combination cycle of that one problem. Yeah. Sorry, what do you mean by change it to another hot structure? Yeah, so if they don't come from cycle classes, we don't know how to prove it, except in this case coming from genus one groups. And there's a few other cases we know how to handle, like this isn't written down, but I think we can prove it for like you take a family of abelian varieties and you take a Taylor expansion around the CM point, I think we can handle that kind of thing. But yeah, in general, I mean, we definitely, I think there's serious instructions for proving this theorem for arbitrary. Very, it's like kind of closely related to small conjectures focus on crystal behavior of the molecule. I think it's probably challenging. Are there other questions? Yeah. Yeah, I mean, what you need is some compatibility between hot theory and getting hot theory. So the only way I know how to do that, I mean, yeah. So I could axiomatize everything I need, like, don't really need it to be a cycle class. You need to satisfy some long list of conditions for Hodge theoretic and Getic Hodge theoretic. Any one of those conditions is conjecturally equivalent to being a linear combination of cycle classes. Yeah, so yeah, really you need something that's weaker than this, but if you can make the Hodge breakdown. Any other questions? Okay, let me tell you the main term of the talk. Hour and a half. Theorem C. Again, same setting, so I have to add pi is proper. Then do again. You just need some finally generated field of characteristic zero here. And then so this data is the analog of the Taylor modern connection we said was the moduli space endoram X over S, the moduli flat bundles on the fibers of this map, mapping to S. This is equipped with the isomonotropic equation. This is the sum linear ODE. If you'd like, you don't lose much generality just by imagining you're in this case. I guess the only issue is I wrote smooth proper there, but in fact, if you look at the paper, we don't make that. So everything I'm going to say works the world's free closed singularity. So in particular, this differential, what I'm going to say applies to this differential thing. So that conjecture is true for Taylor expansions of solutions of leaves of the isomonodromy equation, like the solution for that system dagger, about what are the initial conditions. So E nabla and from XS if E nabla itself is a Gauss monodromy. So in other words, here we prove with the conjecture for Taylor expansions around cycle classes, so cohomology classes which have some algebraic geometric meaning. Here we prove the conjecture for solution to the isomonodromy filiation at points of algebraic geometric meaning. So the non-abelian analog of a cycle class is that's what. Okay, so I'll say a word about the proof, but let me just before I do that, let me say, I mean, it's really the same as the proof in some way. Like the main difference is that this proof is 3 pages long and the proof is 50 pages long. But somehow each line in the 2-page proof just blows up by a factor of 100 or something. Here the proof uses a non-abelian Hodge theory and about characters P and characters 0. And also with some related objects with the Higgs realm as well. So the non-abelian analog of Fontaine pi theory. Okay. So this is a bit more modern than this theorem probably did not have been proved in 2010. Great. So before I say a little bit about this theorem C, I want to try to convince you to care about it. Here's a little proposition, which was kind of my main motivation for working on this. So this is I'm sorry, both of these theorems are going to lab. Yeah, please. Yeah, so this is the fiber of this over the. Yeah. So yeah, so let me try to, before I say a bit more about how one understands this theorem, I want to say why you should care. So there's my main motivation for thinking about this was the following results. I proved in kind of old joint work with Brian Lawrence. So the main conjecture for the main conjecture, meaning this conjecture for moduli space of flat bundles on the universal curve of the moduli space of curve. Equipped with its monodromy equation applies curvature conjecture. For all flat bundles on all varieties. So in other words, there's one nonlinear differential equation, the monodromy differential equation, where if you could prove this conjecture for it, you would prove the curvature conjecture. And moreover, that differential equation is highly structured. Like it's not some random nonlinear ODE, it's one that kind of comes from algebraic geometry. We know a lot about, Hodge theory, non-abelian Hodge theory that we can use to attack this one particular the monodromy equation. Okay, so I claim understanding this is I don't want to claim that this theorem is really progressed with the conjecture, but at least I think it's a fruitful point of view. And I'll in September I'll say a lot more about what we can prove in this today. Great. So I think this is kind of why you should care about theorem C here. So if we could prove this theorem for all initial conditions, we'd have proven p-curvature. We only prove it for very special initial conditions. Nonetheless, there's some evidence that this path is fruitful. Hopefully in September, I'll give you precise conjectures that monodromy that I think are maybe more approachable and would imply the p-curvature conjecture full stop. Great. Are there any questions before I continue? Maybe let me just say a few words about how to prove the theorem B and C, and then we'll probably getting tired. This is the last section of the talk, the proof ideas. Great. Okay. So we're studying some differential equations and some initial conditions with some extra structure. So let me kind of say here, I'm going to prove kind of sketch the proof of theorem B and theorem C parallel, which really are kind of parallel here. So let me remind you. So we have initial conditions in both cases. So here we have let's say a C linear combination of cycle classes. Maybe just to simplify the argument, let me just say we have a cycle class, honest cycle class, an honest algebraic variety. And here we have a Gauss-Monod connection. So these objects have some extra structure, extra properties. They're not arbitrary elements of homology. Property. So in this case, well, if you believe the Hodge conjecture, being a cycle class is the same as being being a Hodge class, so being a element of an integral singular cohomology living in the appropriate piece of the Hodge equation. So n h2i x s d of I second. So I think that's taken for 0 piece of the Hodge equation. If you don't like to put the I here, you could put a F on. This is what it means to be a Hodge class. And here, this local system, the flat bundle, it has the property or the structure of underlying a Z variation of Hodge structure. I claim that these you should think of these as being totally analogous, and in fact, well, the Hodge conjecture tells you that this implies this. There's a non-abelian analog of the Hodge conjecture, the Simpson conjecture, so this implies that. But if you have a flat bundle which underlies the ZVHS, it should be a cosmonic, or at least to some end. So in order to win, you want to do two things. So, well, first there's an algebraic step. Maybe I'll call a local step, which is you want to show that this property or structure extends when you deform the class. In other words, you take this initial condition, you solve the differential equation, you get a local solution, and you want at every point of that local solution for it to have this. You want the local solution. Well, here, being a Z class is automatic. You take a local solution to this thing. Well, the Z cohomology isn't changing, it's topological invariant. So here you want the local solution, you just care about this. You want the local solution to stay in F0. It's flat bundle. And here you want, so the analogous statement here again, if you have a Gauss-Monon connection, when you isomonodromically deform it, the monodromy isn't changing. In particular, if it started having a Z structure, it keeps having a Z structure. So the Z structure is automatic. So what you want is it to remain a CVHS. So you want the Griffiths, you want the Hodge filtration. To prove that you need to show the Hodge filtration on the nabla extends Griffiths transversely to the isomonodromic definition. In other words, solving this differential equation means writing down a family of flat bundles, passing through the one you started with the same monodromy. As the central fiber, you have a Hodge filtration, Griffiths transverse equation, and you need to show that that filtration extends in a Griffiths transverse manner over the whole family. And here, in both cases, what this amounts to is identifying the obstruction to staying in F0 or the obstruction to the Griffiths transverse filtration extending to something related to the obstruction is related to P curvature. So in this case, this is basically due to cats. There's substantial complications where you cannot just use cats. If instead of a cycle class here, you have a C-linear combination of cycle classes. Here, this is so one needs to make sense of the P curvature of foliation and somehow identify the obstruction to Griffiths transverse deformation with that P. I think as far as I know. Okay, and then finally, there's the global analytic step. Okay, so here, well, what do you need to show? You now have a family of elements of cohomology where on every fiber they're a Hodge class. You need to show they have finite orbit under pi1 of the base. Here, that's consequent from the theorem of the fixed part. Okay. Here, so here what you want to show is if you have a family of flat bundles on every fiber, they underlie ZVHS, then the total space of that family, so the leaf is algebraic. So I would say this is arguably due to Deligne, but first written down explicitly by Kenta. flow in the quasi-projective case, with some extra ingredient which Josh needed that I need to prove, and then I know Kurt's prove some version of this at the same time. So what you need to show is that if you have a family of flat bundles, which remains as EVHS under monodromic deformation, then its conjugacy class of the monodromy is finite orbit under pi1 of the base. And that's what many different approaches. That's the idea. Okay. So in September, I'll tell you how to prove not how to prove the P curvature conjecture, but how to prove a version of the P curvature conjecture for these fools. Doesn't quite imply the classical P curvature conjecture, but I can be some different analog of Katz's argument. It's not another setting. Right, I think that's all I want to say. Yeah, sure. Yeah, so I say this. Great. Maybe I'll just do the linear case first. So suppose you have a solution to a Gauss-Model connection, so a family of homology classes, and at every point it's a Hodge class. Well, what that says, in particular, it's an element of integral cohomology. So its orbit of the pi1 under pi1 of the base is discrete homology. And it also kind of stays in, I guess the way I've indexed things in H00, HII, which has a unitary, a positive definite permission inner product on it, which is clear by the monitor. That means it has compact orbit under pi1 of the base, and a discrete compact set is finite. What we've just shown is that this homology class is finite orbit under pi1 of the base. You know that in particular it's finitely branching. If S is proper, a finitely branching function on a proper variety is automatically algebraic by Riemannian existence. If S is quasi-projective, you need to use the theory of regular singularities by algebraic, but you're 99% of the way there once you prove this finite orbit property. You should understand this as a completely analogous thing. One way of saying this is, okay, you have your flat bundle that underlies as EVHS, and in the local step, we show that all the isomonodromic deformations also underlie EVHS. So now you have your flat bundle, you analytically continue it around a loop in the base, you get another flat bundle with the fiber you started with, it also underlies as EVHS. And Litt showed that there are only finitely many local systems of a given rank and variety which underlie the EVHS. So what we've just shown is that the orbit of this local system under pi1 of the base, finite. So again, you've got some finite branching, and that's 99% of the way there to proving it's algebraic. That's why I attribute this to Litt, but one has to do a bit more. Maybe I should add Simpson's name in that list. By the way, this theorem of Litt that there's only finitely many ZVHS on a given rank on a variety, you can prove in one line. Not very. So the local step is pure deformation theory, and the global step is analytic. The global step is analytic. Oh yeah, that happens in the local step. So here I have these two things I'm trying to prove, and what I want to show is the obstruction is identified in some way with the P curvature. So this condition here tells you the P curvature of the foliation kind of vanishes to high order along your lead. And that's enough to prove the vanishing of this obstruction. Yeah, so the arithmetic is purely in the formal neighborhood of the problem. Yeah, I'm sweeping a lot under the rug like that. So what I just said is enough, I think, to probably reconstruct the fact that the Griffiths transverse filtration extends to the first order neighborhood of the monodromic deformation, but somehow most of the work here is to do the higher order neighborhoods, and that there's some really quite substantial arguments involving subversion of T1 lifting theorem. It's kind of not trivial. Yeah, please. So P curvature. Yeah, that's right. Yeah. Yeah. So if I want to assume my initial condition is an honest cycle class, you can really just use. Yeah, that's right. Yeah. But it's much harder if you just assume it's a linear combination. Like, then you need. I think there's sort of theoretical reasons to think that you cannot have a pure characteristic P argument. You need P-Hodge theory. And so yeah, we use like Katz's formula is kind of it's contained in fundamental pi theory. Yeah. So the non-abelian Katz formula is for down. That's for down. Yeah. Yeah. So here here it's just fundamental pi. Yeah. So somehow what you need to do is you need to use the integrality of the Taylor expansion to say that to understand like yes, you have the crystalline Frobenius. What you know is that at your initial condition, it multiplies your like initial condition by p to the I. That's what the consequence of being a cycle class. If you have a linear combination of cycle class, it multiplies by p to the I and does some Galois twisting on the coefficients. So once you know that, you know that's actually true, well, on the initial conditions and on the whole formal solution, right? Because the formal solution is like a slab section to the flat bundle is determined by the initial condition. So what this means, what having this integral solution means is that like your Frobenius twist of your class is p to the I times something. And then fundamental pi theory tells you what that means, that when you reduce mod p, your initial thing was in some piece of the Hodge filtration. And since that's true for infinitely many p, you win. But yeah, because of this p to the I think you need to care like a mixed character argument. I think you can't just use canons. Yeah, it's sort of there's a stronger statement in as part of fundamental pi theory that encapsulates Katz's. Yeah, if you'd like, you can think of Katz's formula as being the statement that you're a one periodic under the Higgs-Bound flow. Fundamental pi theory is the p-adic. Katz's formula is here. Fundamental pi theory is the same statement. Yeah. Yeah. Yeah, it's kind of the converse to the theorem of the fixed part, right? So the theorem of the fixed part says that if you have something like the stuff with finite orbit under pi1 of the base is a subhot structure. Here I'm saying that if you are a subhot structure, you have finite orbit under the base. That's yeah. So really, maybe I should have the converse to it. Yeah, and the theorem of the fixed part is an if and only ends using one direction. Are there any questions online? Or we're coming from elliptic curves, yeah. 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 So I mean, so right. So that we proved it for arbitrary initial condition. So yeah. Yeah, this is for arbitrary Gauss-Model connections. We can only prove it for cycle classes, but for things coming from families of genus one curves, okay, and some long list of other cases, which I'm not going to write on the board, we can prove it for all initial conditions. Basically, it's because we understand well. Like, I mean, the main point there is that the Hodge filtration, the non-trivial piece of the Hodge filtration is one-dimensional. That makes it very easy to understand its behavior. I think if you have a kind of higher dimensional Gauss-Model connection or higher dimensional Hodge structure, you need to understand well how the Frobenius interacts with the Hodge filtration. Yeah. So yeah, you can ask, yeah, for example, can you prove some version of this conjecture with solvable one? So yeah, I definitely just the existing proof for the Kramer conjecture just gives you this in rank one. Like this conjecture is known for rank one linear ODE. I would have to think a little bit about the solvable monodromy case, but my expectation is that Bosch's proof of the peak curvature conjecture in the solvable monodromy case probably also actually applies. But yeah, there's I think getting one if and only if two is pretty easy from what Bosch does, but getting three implies one sounds like it might be a bit trickier. I haven't thought through the details, so I don't want to claim it's median. Definitely doesn't follow from Bosch as written. We would have to kind of execute the argument again. Yeah, I would say being a geometric origin. I would say some end of a Gauss-Monon connection by definition an OD geometric origin. Yeah, so being in Gauss-Monon connection is a bit stronger, right? So for example, it implies you have a Z structure, whereas some ends of Gauss-Monon connections might not. And yeah, I think there's a number of conjectures about when a linear ODE is of geometric origin. So for example, having nilpotent P curvature is supposed to imply a geometric origin. I think it would be very interesting to find analogous conjectures for being a kind of non-abelian geometric origin. So like characterizing isomonodromy differential equations. Yeah. One interesting thing is they do not have nilpotent. Oh, so yeah. So let me tell you. So and for me, it's just a foliation. But let me say what a foliation is. So X is a smooth variety. F inside of its tangent sheaf is a subbundle. It's the definition of a foliation or integrable foliation if closed under the Lie bracket. And so a leaf is a map, so an analytic map. So maybe complementary. It's at the X that natural map to the pull back to the X after through pull back to the F. So yeah, so I mean the picture is that you have your variety at each point, you have some subspace, the tangent space that you're trying to integrate them. Here, I mean, the theorem of Frobenius that under this condition you can always integrate them to get an analytic submanifold. And the question is when is that analytic submanifold, or sorry, not submanifold, an immersed analytic submanifold. When is that analytic subobject actually an algebraic subvariety? So here, I guess I didn't state the conjecture in that generality. So I was trying to be elementary, but what you can do is just take the formal completion of your analytic submanifold, look at its structure constants, act as that formal completion, descend to a finite the algebra. And here the analog of the conjecture in this setting is that this Z is an algebraic subvariety of X, if and only if the formal set to a finite identity. So the connection is just this foliation. The connection is this foliation. So the analogous thing you should think of is you have a flat bundle on some X, sorry, a flat bundle on some S, take X to be the total space of the flat bundle, and then poke the foliation. There's a foliation on that total space which captures the safe data. Yeah, so yeah, let me give you the example. So here's this is why this is a generalization of a connection. So example, if you have B nabla with the flat bundle on S, with the total space of E, and there's a natural, yeah, this is X, natural foliation inside of this. Basically, how do you figure out what is like the subspace of the tangent space of X? It's like you take a formal solution to your flat bundle and you take it to it. Yeah. Yeah, so you can look at, for example, or so in this here, this is a totally general kind of object. Look at the totally general kind of relation. You can look at the following situations. You can look at x to s. So the one way of getting a foliation is you have this, let's call this f, the derivative of f is a map from px to f star ds. This is smooth, the short sequence of this, right? And the kind of foliation we have here is a splitting. The subsheet comes from chosen splitting. So this is something, which is respect to the algebra structure. This is some class of foliations called horizontal foliations. But this conjecture for horizontal foliations is equivalent to the conjecture for arbitrary foliation. Have general foliation. You can locally choose a map to some base where it's horizontal. So the conjecture is about arbitrary foliation, but the theorem is about monodromy foliation. So it's just it's like being a Gauss monodromy connection. So there exists. So you are isomodromy foliation if there exists some family over S, so that you are M rom of X over S with its isomodromy foliation. So to prove something is an isomodromy foliation, I don't know how to recognize it abstractly. Just like give me a family, and I construct out of that differential equation. Yeah, I mean, it's definitely a very special class of ODE, but the point is that it's general enough to capture the controls all the arithmetic of all linear ODE. Yeah. No. It's much more special than that. Yeah. You should think it's really a very just where we know how to prove. It's like the only nonlinear ODE that I know how to prove anything about. I think arguably the only nonlinear ODE that anyone knows how to prove anything about. Still has this extra algorithmic stuff there. Yeah, I think proving this conjecture for like any nonlinear ODE which doesn't have an algebraic geometric meaning would be a huge thing. Any other questions? All right, should we call it a day? This is the question. Yeah, so it does actually follow. It's a little tricky. Yeah, so right. So how do you do it? So you take so first of all, you can reduce Katz's theorem to the got it. How do you get that? Yeah, I do not actually know how to do that. I think it neither follows from nor implies. Yeah. Yeah. But the point is that Katz's theorem has a much stronger hypothesis, right? So it's basically the hypothesis is that Taylor expansions of all solutions at all points satisfy free. And then he shows that all solutions are great. So it somehow, yeah, it's both a much stronger hypothesis and a much stronger. It's not as related. Yeah, I don't think it's so obvious. So definitely. Oh, no. Okay, I see how to do it. Okay, I see how to do it. So to prove Katz's, yeah, let me do it. Okay. Let me prove Katz's theorem. So first of all, to prove Katz's theorem, it's enough by Lefschetz to prove it when the base is the curve. So now let's yeah. So now you get a Gauss-Monod connection on the curve. In other words, you get a point of this base. And the fact that the P curvature of the Gauss-Monod connection is 0 tells you the Taylor expansion of that point satisfies 3. That's not obviously true computation. In other words, we have a Gauss-Monod connection satisfying 3, and I proved the theorem in that setting. So in other words, the leaf of the monodromy relation through that Gauss-Monod connection is algebraic. So in general, it is not true that having an algebraic leaf of this foliation implies that the monodromy is finite. What you want to think text. But it is true if G is really big compared to the rank of the local system. So what you can do is at the very first step, go back to a curve of incredibly huge genus, use our theorem to get a algebraic leaf of the monodromy foliation here, and then use the fact that if G is very big compared to the rank, the leaf being algebraic implies to a finite monodromy. So that is a way of deducing it. It's a bit roundabout. Yeah, I don't know a software. Yeah, it seems a little challenging. Thank you, those of you who are online.